let's do this. That was very enthusiastic. We have, if I'm looking down, that's because the assignment is there on my device, that once in a while I'll do this to make sure the screen doesn't turn off. Our first assignment, this is dealing with the central limit theorem and starting to get into hypothesis testing. First question, you have a population of 5 observations. Is that possible? Sure, you could have a really rare genetic disease or something. In psychology, it's not very common, but theoretically, you can picture this, a population of 5 members. Okay, I've measured reaction times, mean reaction times for each 5 of the members of that population. And my first question is compute mu and sigma. Okay, well, mu is easy, the mean of a population. I didn't even write down the formula, but you know this. You add up these 5 numbers, you divide them by 1, 2, 3, 4, 5. Okay, mean 390 milliseconds to be precise. Okay, I think that was the easy part. Standard deviation, not variance, standard deviation. Why again? Standard deviation, because if variance is squared, so the variance of these numbers would express reaction time squared. I don't know what that is. Like, how useful is it if you would say, it takes me 10 squared minutes to drive to RDP? Yeah, so what do? Take the square root of the variance, and then everything is back in minutes, or in this case, milliseconds. Okay, well, in this case, let's start using that computational formula simply because it saves so much time. Otherwise, we would have 300 minus 390 squared plus 330 minus 390 squared, and it just keeps going. So, what do we need for this computational formula again? We need the sum. This is a strange... sorry, oh no, that was supposed, no, I didn't want that there, sorry. So we have these 3 things here that I already wrote down because we'll need them. We have the sum of all x's, 5 x's. We have the sum of all x's squared, and then we have the sum of all squared x's, and those are different things. So just looking at what I get, and for this I'm just looking down at my monitor there. The sum of all x's was 1950. I think I'm willing to believe that. 500, this is 900, this is about 1300, and then about 6. Yeah, it's about 1950. Do a quick check, right? Just so you know that you're on the right track. Okay, then I have the sum of all x's squared. Okay, the sum of all x's squared. And then I have the sum of all squared x's. So to compute this value, I would take 300 squared plus 330 squared plus 400 squared plus 420 squared plus 500 squared. That should be a pretty big number. And it is. It's 700. I'm just double checking I can read this properly. 785,000 because I am getting old. And 300. And then finally I have the sum of all x's squared. I add up all the x's. I've already done that and I square them. So 1950 squared, that would be a really big number. 3,802,500. Okay, well this I can plug into my formula. I have the sum of all x's squared, 785,300 minus the sum of all x's squared, 2 and 500. Am I still more or less? Yes, I'm still visible. And then I divide it by big N. Well, that's 5. There are only 5 observations. So divided by 5, and then this whole thing divided by 5 again. And of course, this was meant to be a sigma, not a variance, so I must take the square root. Otherwise, I have the variance. Okay, well, this I can do. I'm just going to read you the numbers in between, but I'm not going to write them all down just to save time. This should come down to 24,800 divided by 5. Then you get 4,960. You do have to take the square root of that, and then you get 70.43. Okay, 70.43. I have sigma and I have mu. I have answered my assignment. Okay, I'm just going to scroll down a little bit. Now, the next question starts to make you think is supposed to start making you think about sampling distributions. So imagine that I'm just reading the question. I draw. No, I'm not. Don't imagine that. I am. The question starts with imagine. It's been a long day already. Imagine that I draw every possible sample of n equals 3 from this population of reaction times, and I'm doing that to compute, or actually to construct, I should say, a sampling distribution of the means, calculate the standard error of the mean for that sampling distribution. Okay, so what I would be doing is draw every possible sample of n is 3 observations that I can. I know we've done that in class, but just to remind ourselves, so what we would be doing is I would say, okay, I take 3 of these numbers, has to be random, right? Take 3 of these numbers, compute their mean, and write it down. And then, let's say that that's right there. I take 3 other random numbers, I compute their mean, I write it down. I take 3 more numbers, compute their mean, write it down. I take 3 more numbers, compute their mean, write it down. 3 more numbers, mean, write it down, compute, write down, compute, write down, compute, write down. And at some point I'm going to have a sampling distribution which is going to look something like this. So every bar, I know this is a very quick sketch, but every bar here is a frequency, but not a frequency of a person's mean, but of the mean of a sample. And you count how often you found that sample mean until you have drawn every possible sample you can draw from that population. Again, refer back to the class slides if you found this a little nebulous, but I mean, that's what we have done. Now, the idea, of course, is, I don't know if that's of course, the idea, of course, is that the mean of this sampling distribution, which gets, that's very unclear, I'm sorry, which gets the symbol mu sub x bar, mean of means, right? So the mean of this sampling distribution will be the same as the mean of the population. And I hope that you now think, of course. After all, this population has a mean, and if I draw every possible sample I can draw from that population every time I compute the mean, then at some point, the mean of all those means is going to be the mean of the population again. After all, I have drawn every sample I could out of that population. Hope that makes sense. If not, then you need to think more about that. Now, this sampling distribution of the mean, the SDM, also has its own standard deviation. Standard deviation at this point, you should be able to think about that relatively easily. I have a normal distribution, it has a mu and it has a sigma, or an m and an s if you like. Right? It has a mean, a standard deviation. Well, the sampling distribution of the mean also has its own standard deviation, but we give that its own symbol because it's special, and we give it this symbol. It's a sigma sub x bar, and we call this the standard error. In this case, the standard error of the mean. Had I not computed means of all those samples but medians, then I could also plot the frequency of all the medians, and this would be the sampling error of the median. But we're not going to do that in this course. We're only going to use the standard error of the mean. Okay, how do I compute that? Well, that is relatively simple. All I need is the standard deviation of the population, pizzazz, which I have right there, and I divide it by the square root of big N. Big N being my sample size, not the size of the population, because I may not even know the size of the population. But I do know that every sample that I drew randomly had the same size. That's the rule of the game. You can't have a sample of 2 and a sample of 3 and a sample of 5. That's cheating. Okay, so I can fill this in. Pretty easy, actually. 70.43 divided by the square root of big N, and big N we said was 3, according to my question. I'm just looking to see if I did indeed ask for 3. Yes, I did. And then the outcome of this is 40.66. Yes. You can do the math. Make sure you enter this in your calculator properly, because I see that go wrong with students, that they divide 70 by 3 and then they hit the square root sign, but then you take the square root of that fraction, right? So make sure that you understand how your calculator works. That's not meant to be funny. Like, sometimes that goes wrong. Then make sure that you ask someone, like me, to guide you. Okay. standard error of the mean. Boom. I'm going to clear some stuff. And I'm going to write that down again. So now we have a couple of things. We have sigma. One of these days, the whole thing will come down. We have sigma, 70. We have mu. And we had sigma sub x bar, the standard error of the mean. Sorry, this is illegible. I'm sorry. I'm at a weird angle. And this was 40.66. Yeah. Okay, now the next question, question 3. So far, so good, right? We can do this. Question 3 is, what would be the effect on the standard error if I would increase my sample size to 4 or decrease my sample size to 2? Now at this point, I first want you to think. Don't just start computing, think. What is a more reliable sample? Remember the central limit theorem and the law of large numbers. A bigger sample will always provide a more accurate representation of the population. Of course, of course. Think of the grades for this course. What do you think is a better indication of how people did in this course? If I ask 2 random students out of 90 for their grades, or if I take 20 students and ask them for their grades? Those 2 students, they could just be super high, super low, right? But 20 students, they're going to be some mediocre ones in grades, not in you. They're going to be some very high scores, some very low scores, right? So every kind of score will likely be represented just based on probability. Boom. Okay. So let's do the math then. Because what I would expect is a bigger sample is going to be a better representation of the population. But if that's true, then the next logical conclusion is, wouldn't I expect the standard error to be smaller if my sample is a better representation of the population? And wouldn't I expect my standard error to be bigger, more variation, if my sample was a poor measure of the population? And is that what we find? Okay, well I can do that. 4n equals 4. Standard error of the mean equals, well, my population mean divided by the square root of my sample size. And I'm quickly looking at the, in Dutch game shows, we would quickly look at the jury to see if my answer is correct. 35.22. So you agree with me that indeed, as sample size increased, this was based on a sample size of 3, as sample size goes up by just 1 more person, my standard error has dropped from 40.66 to 35.22. Indeed, bigger sample, more representative, better representation of the population. Boom. Okay, then for n equals, what else did I ask for? 2. Okay, so now smaller sample. Smaller sample, less representative. I bet you it's going to be more variation, and therefore that sample is a poorer reflection of the population. Okay, well, let's do it then. Standard error of the mean. Well, same formula as before. Well, not this. You know the other formula. You know the one. The sigma that we started off with. This sigma, the standard deviation of the population, divided by the square root of the sample size, and that's going to yield 49.80. Okay, so sample size dropped by just 1. Standard error has become substantially bigger. So you see again, law of large numbers. It works. You see it demonstrated here. Bigger sample, always better. Okay, now we're going to do something a little different. So I'm going to get rid of some of this stuff. That stuff is foul smelling. Okay. Oh. Clean slate, more or less. Not everything has to be gone, but some of these things should be gone. Okay, good enough. Okay, what is our next question? Our next question is screen locked, log in. Okay. Please construct symbolic, so use mu sub 1 and mu sub 0 null and alternative hypotheses for the following hypothesis. I expect that students at RDP obtain higher average stats grades than students at U of C. Okay, I have two hypotheses. I'm doing hypothesis testing, and this is going to become so much clearer when we work on actual inferential statistics, but for now, I'm going to say, follow along. That's the stats cat. Okay. She's very engaged when it comes to statistics. Okay, I have a null hypothesis. My null hypothesis is a null hypothesis. It states there is not going to be any difference between my two populations. In this case, RDP students versus U of C students. Okay, well then if I'm going to use mu sub 1, mu sub 0, it doesn't really matter which of the two I call which. There's also a dog down there that's trying to kill the cat, so this is going to be a very interesting video here. If I'm going to use that, these mu's just represent the mean of a population. You already know that. Mu is the mean of a population. Okay, so I have a mu sub 1, say, and a mu sub 2, or what I asked for, mu sub 1, mu sub 2. Okay, well, a null hypothesis suggests that there is no difference between these two means. So, the mean at RDP is the same as the mean for U of C. This is what I would say. And if I formulate this as a null hypothesis, then what I'm saying is these two means are identical. And the reason I wanted to start this way is that I can show you why null hypothesis is called a null hypothesis. If these two means are the same, then you must agree with me that mathematically mu sub 1 minus mu sub 2 equals 0. They're the same number. Let's say 2 and 2. 2 minus 2 is 0. That's where the null in null hypothesis comes from. Now, having said that, in this case, I wouldn't start with a null hypothesis. I would start with my alternative hypothesis, because in this case we have a slightly different situation. I never said one population was the same as another one. Let's reread the question quickly. Hypothesis is I expect the students at RDP obtain higher average stats grades than students at U of C. Okay, then I'm going to start with my alternative hypothesis, H sub 1 or H sub A, doesn't matter. You see both of those sometimes. And what I'm saying now is, I know I have two populations, RDP and U of C, and I expect that students here have higher grades than there. Higher grades. Boom. Done. This mean is bigger than that mean. And if you start that way, it's much easier to come up with the null hypothesis. Because then I just say, okay, I have mu sub 1, I have mu sub 2. The null hypothesis must be the exact opposite of an alternative hypothesis. Because remember, they have to be mutually exclusive. This is true or that is true, but they can't both be true at the same time, because then I can't reject one or the other. Okay, so then what happens to most students, they now say smaller than. That's almost correct, but not entirely. The correct null hypothesis is smaller than or equal to. Think about why that equal to has to be there. Did I not just say this? Mu 1 minus mu 2 is 0. That's the equal to. And certainly, if you find that a little difficult, if you say, yeah, but wait a minute, equal to, then that leads to all kinds of confusion I've seen in the past, because then students say, oh, but then they should also be equal to. No. That's not mutually exclusive. This is equal to, or this is equal to, but if they're both equal to, they're no longer mutually exclusive, because then I'm saying 2 equals 2, 2 equals 2, or 10 equals 10, 10 equals 10, doesn't matter, two the same numbers. That's not mutually exclusive. So the or equal to always goes in the null hypothesis, because remember, equal to means there is no difference. Here I'm saying students at RDP obtain a lower than or equal to stats grade as U of C students. And what I hope to find is that this is not the case. Because if this is not the case, then I may reject the null and accept my alternative hypothesis, and then I have shown, indeed, RDP students had a higher grade than U of C students. And that's it. That's how you do this symbolism stuff. I think that's the easiest way to do it, to start with the alternative, because that's what you're interested in. And usually you have the clearest formulation for that. And there are many considerations. Some people say null hypotheses are kind of useless because what's the probability that two groups have exactly the same mean? It's basically zero, so you will never find that. And that's why later on we will see that you can't just say there is a difference. The difference has to have a certain size for it to be significant. But that's getting way ahead of ourselves. Let's first do the final question for today. Consider your answer to question 4 that I just erased. Is this an example of a directional or a non-directional hypothesis? Why? Okay, so we quickly reproduce what we had. We had an H0, we had an H sub 1, and I said mu1 smaller than or equal to mu2, and I said mu sub 1 larger than mu sub 2. Well, is it directional or is it non-directional? Directional, of course. That is the direction. Bigger than. Whenever you say, see, the dog is now trying to murder the cat. Whenever you see something like bigger than, smaller than, faster than, slower than, whatever, that type of comparison, directional. Immediately go there. And now if you struggle a bit with that, then let me show you what a non-directional hypothesis would look like. That's what I started off with. Very simple. We just get rid of this, the middle part. A non-directional hypothesis would state something like this. I believe that the stats grades at RDP and U of C are not the same. I don't know how they will be different. Now you may say, well, are you an idiot? Like, what? How can you not predict anything better? No, not necessarily. In some cases, it's very easy to predict. For example, if you're testing a new antidepressant drug, so an antidepressant, obviously you would predict a directional hypothesis. After taking this drug, people with depression should feel less depressed. And the null hypothesis, no difference in control condition, experimental condition, the drug and the placebo, for example. But in other cases, I don't know, like say something like, who do you expect to have more headaches? People with depression or people with anxiety? I really wouldn't know what to expect there. And if you want to make that more psychological, who would you expect to have a shorter reaction time, so be faster on some sort of reaction time task, like say a Stroop task, assignment task, whatever. People with depression or people with anxiety? I wouldn't know what to predict. So in such a case, you may be limited to something like this. And some people even say you should always do this. But I'll try to mention that when we get to that point. Now, we have our H1. What about H sub 0? What is the opposite of this? What is the opposite of not equal to? Equal to, of course, of course. Problem solved. This is a non-directional hypothesis. Non-direction. Is there this, 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 this? No. And therefore, non-directional. I don't know what to predict. Could be shorter than, could be faster than, could be lower than, could be higher than. I don't know. All I know is that there will be a difference. Non-directional. Another one bites the dust. I hope this was useful. Let me know if you have any questions. I'll see you soon.